Okay, class, what we're talking about now is concentration of the urine. How do we concentrate the urine? So this is what we're looking at now. Okay. The juxtaglomerular nephrons with their very long loops. Now remember, the juxtaglomerular nephrons were located down deep, right at the edge of the cortex with the medulla, along with the vasa recta, those straight vessels. They are capillaries. Set the stage for concentration of the urine. So that's what does it. Okay, these here. All right. So when we look at it, remember everything is going according to osmolality. We talked about that a little while ago. Okay. So let's see what we got here. The nephrons create a hyperosmotic interstitial fluid environment. Okay. Here's the interstitial fluid outside. We're going to be talking about that. All right. This symbolizes the collecting duct. This is the loop of Henle here. See how close these are? All right. So when we look at it, the nephrons create a hyperinterstitial fluid environment around the tubules. Especially the collecting ducts in the deeper areas of the medulla. Especially the collecting ducts down in here. See? That osmotic pressure is increasing. See, that's the cortex, that's the medulla. Take a look. In the deeper areas of the renal medulla. The hyperosmotic environment is accomplished through the physiological processes known as the countercurrent exchange system and the countercurrent multiplier system. Okay? The countercurrent mechanism. There are two systems. The countercurrent multiplier system and the countercurrent exchange system. Okay, those two systems. Now what I have done is I've inserted a link to a nice video that you can look at how these systems work. But this countercurrent multiplier system and countercurrent exchange system are responsible for creating this hyperosmolar environment. That we're going to use. And the movie will show you how those two systems work. Okay, let's go further. It is the fact that the collecting ducts travel, see here, down through the hyperosmolar environment. Look how the collecting ducts, he has to come down. Travels through that hyperosmolar environment because now you remember the collecting ducts come together and make a papillary duct. So the flow has to be going straight down through this hyperosmolar that allows them to concentrate the urine. Okay, here we go. If the urine is to be dilute and no water removed from the final aspect of the modified filtrate. Why do I call it modified? Because previously you've already done reabsorption and secretion. So the filtrate initially was changed along the way. As it transcends down the collecting duct. So if the urine is to be dilute, no water removed as it comes down, then no water doors, which we will call aquaporins 2, will be inserted in the collecting ducts. Thus, no water can get out. Without openings to allow the water to be sucked out into the surrounding hyperosmolar. Remember I said the hyper side acts as a what? Vacuum for water. Without openings to allow the water to be sucked out in the surrounding hyperosmolar environment, all the water remain in the tubules and be urinated out. Okay, so you'd have a lot of urine coming out. If the urine is to be concentrated and water removed from the final aspect of the modified filtrate as it transcends down the collecting duct, then water doors, aquaporins, will be inserted in the collecting duct membranes. These openings allow the water to be sucked out into the surrounding hyperosmolar environment. It'll be sucked out. Hyperosmolar, hyperside expo vacuum of water. Thus, minimal water will be left. Let me put B here. Thus, minimal water will be left in the modified filtrate. And the person will urinate out little water. They will urinate out just enough water to solubilize the waste that must be in an aqueous mixture. Now, remember what I told you. Waste coming out through the kidneys needs to have some water with it. It would be toxic if it's too concentrated. Now, to go to a subject, birds can put out more concentrated urine than humans can. But that concentrated urine, think what it does to your car if it gets on it. Okay? But even birds have to have it in some water. Okay, we go further. When to concentrate and when to dilute the urine. Now, we showed what happens to concentrate. Put water doses in, it becomes concentrated. Put no water doses in, the urine is dilute. Okay? So the question is, when to concentrate and when to dilute the urine. Okay, let's see. Remember that blood osmolality is about 270 to 300 milliosmolal. In order to keep that osmolality, urine is diluted or concentrated, quote, accordingly. If the blood osmotic pressure is rising or is high, if the blood osmotic pressure is going to the high side, it's coming. See, about a 285 is median. So about 285 would be a median value. So if the blood osmotic pressure is starting to rise above, let's see, that median value, okay, more water should be retained by the body because we have to deconcentrate, I guess I'll use that term, the body solids. Thus, concentrated urine because you're holding the water back to drop the osmotic pressure. If the blood osmotic pressure is lowering or too low, then the urine, okay, should be dilute because now I need to get rid of a lot of water in order to concentrate the solutes in the blood. More water should be urinated out. So it has to do with, so the whole thing of how much you put out, how much you don't put out has to do with maintaining this normal osmolality of the blood. Okay, let's go further. So what's the major thing that's doing it? Antidiuretic hormone. The osmoreceptors in the hypothalamus can cause the posterior pituitary neuroendocrine cells. Now, the posterior pituitary neuroendocrines, there are two nuclei. One does the ADH, also called vasopressin, and the other does oxytocin, that stuff that make. But those cells are neurons, but they do endocrine work. Neurons, but they do endocrine work. They're neurons. Okay, the osmoreceptor can cause the posterior pituitary neuron to secrete ADH, antidiuretic hormone. And think what the word says, antidiuresis. See, the two words for urination, fancy, are diuresis, Latin, natriuresis, Greek. Now, think about this then. A long time ago, they realized that sodium, this substance, sodium, did a lot for how much you urinate or didn't urinate. So they gave it the name natrium. See, from natriuresis, that's why it's Na. So in response to high blood osmotic pressure, ADH will be increasingly secreted to cause the collecting duct to insert aquaporins too, because we want to retain water. The receptors in the collecting duct for ADH are the principal cells we mentioned. Water is sucked out in the surrounding hyperosmolar environment. When the osmotic pressure of the blood is low, the opposite will occur. Less ADH is secreted and more water urination occurs. So this gives you an idea, and see, the further down you go, because of that countercurrent multiplier, the higher the osmotic, so and see, it's got to go through all that. So the more doors, as it goes out, it sucks even more. It keeps the solution around here salty. But the movie I'm going to give you the link to right after this video can explain and show you how that countercurrent multiplied countercurrent exchange system creates this hyperosmolar environment. But the movie and my videos and my PowerPoints cannot replace you reading on it. Remember, always remember that. All right. Now, so we talked about that. So I'll just say a few words here. Okay, let's go here. So we have these things called the diuretics. Make you diuresis. Chemicals that enhance the urinary output. Okay. There are many different kinds. Osmotic diuretics, like high glucose. See, high glucose in the blood makes you urinate a lot. That's why people with diabetes can have polyuria if the blood sugar gets high. Because remember, think about it. If you recall, if you don't reabsorb in the proximal convoluted tubule glucose, it'll be in the urine. But if it's in the urine, if it's going down the tubule, it gives the tubules a hyperosmolar. So not as much water comes out. Since not as much water comes out because the glucose is there, you urinate a lot. Alcohol, drinking alcohol, inhibits ADH. That's why people urinate a lot while drinking. Caffeine and other diet inhibit sodium ion reabsorption. Okay. Lasix is a very powerful diuretic. It inhibits sodium-associated symporters. So you lose a lot of sodium. You also lose some potassium too. So now potassium, I'm going to say this to you. Potassium is the main thing that's really lost with those diuretics. That's why when people with high blood pressure on diuretics, they'll be told to drink orange juice or eat bananas or even get some potassium. Because potassium, remember, is the thing that can do you in the most. Okay, potassium is the electrolyte that if it gets low or high is the one that will do you in the quickest. Always remember that. Okay. So that's kind of a little bit on that. We've already talked about renal clearance, so I'm going to close this video out and let's see where we go next. We're going to talk about urine a little bit.